Hi, in this video, let's discuss one of the laws of exponents. So let's recall this exponential notation. Suppose a is a number, n is a positive integer. Then recall when we write a to the n or a raised to the n, that is simply a shorthand notation or an abbreviation for this arithmetic expression where a is multiplied by itself and we have n of those a's multiplied by itself. So that's what it means. Now with that in mind, let's look at what I have here. I have 3 to the 4, which is a number, and do not pull out your calculator and calculate what 3 to the 4 is. Just keep it in mind, 3 to the 4 is a number, and here 3 to the 5 is a number. I would like to multiply 3 to the 4 by 3 to the 5. And let us use this exponential notation, and let us begin to rewrite this expression as follows. 3 to the 4, remember by our definition, is simply a shorthand notation for this arithmetic expression where 3 is multiplied by itself. And look, 1, 2, 3, 4 of them. That 4 corresponds to this exponent of 4. Times, instead of 3 to the 5th, I unwrap it and I recognize 3 to the 5th is simply an abbreviation for this expression where 3 is multiplied by itself, and I have 5 of those. 1, 2, 3, 4, 5. So look at this expression. It is simply multiplication of numbers, which we know we can carry it out in any order. We don't need this parentheses. So that's what I wrote out here. This is simply multiplying 3 by itself, 4 times here, and then continue to multiply 3 times it by 3, and here I have 5 more 3's. That's what this expression says. I need to multiply 3 by itself, 4 plus 5 number of times. So I do not want to write 3 times 3 times 3 times like that, 4 plus 5 or 9 times. So I simply put dot dot dot, and here I could have written 9 times. I simply wrote 4 plus 5 just to help us remember. The 4 comes from here, the 5 comes from here. So I have 4 plus 5 times. So now this is a long expression where I'm taking the same base number 3, multiplying it by itself many times. Once again, we apply the definition to wrap this up into a very shorthand notation, which is the base number. I write it here. How many times am I multiplying it by itself? 4 plus 5. That 4 plus 5 goes in the exponent. And now you can write it as 3 to the 9. So here what we're concluding is 3 to the 4 times 3 to the 5 is a number. I'm not so much interested in exactly what number that is, as in if you used your calculator. But this work helps us think that 3 to the 4 times 3 to the 5 is simply the same number as 3 to the 9. And here's all of the logic, and remember how we used the definition to arrive at this logic. This 9 by our steps is really this 4 plus 5. Those exponents are getting added. So keep all of this logic in mind, and we'll discuss some more examples now. Let's look at this example. Suppose m and n are positive integers, and let's look at this expression 3 to the m times 3 to the n. We just finished discussing 3 to the 4 times 3 to the 5. So here I've generalized that example. I've replaced the 4 and 5 by m and n, and let's see if we can keep the logic going. Remember, the trick is to always use this definition of exponents. So 3 to the m is simply a shorthand notation for 3 multiplied by itself. When we had 3 to the 4 in the last example, I simply wrote out here 3 times 3 times 3 times 3, 4 number of 3's. Here when I have m, well, m is some positive integer, mysterious positive integers. I'm not telling you what it is. So then how do we write that expression? How do we unwrap this? And here's the trick I've been talking about. We use this dot dot dot. So I don't exactly write out how many 3's. You can simply start out with a bunch of 3's multiplied together. Put a dot 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 times 3, end it that way. and underneath you say n times, and that's our notation for, oh, I'm just multiplying 3 by itself, and it's m number of those 3's multiplied by themselves. That's what that means, and I'm getting that directly from the definition of exponents. Now very similarly, 3 to the n, unwrap it, and that's really this expression. Now here, just as in the previous example, we notice we are simply multiplying 3 by itself. We don't really need these parentheses anymore. So because all we're doing is multiplying 3 by itself many times. So that's what I have here, multiplying 3 by itself many times. Again, look at the dot notation. How many times am I multiplying it by itself? Well, here I have m of those, here I have n of those. Combine them. So that's m plus n. The m is this number. This n is this positive integer. Now look at this. This is a long expression. It sure looks like this expression. Like we said when I introduced exponential notation, I said such arithmetic expressions can be abbreviated into a very nice shorthand notation. What is that? Since we're multiplying 3 by itself, that is the base number 3. And how many times am I doing that, multiplying 3 by itself? Here there are m plus n copies of those 3's multiplied by themselves. So that m plus n goes in the exponent. So look at what we have. We're saying 3 to the m times 3 to the n. This expression is simply exactly the same number as 3 raised to the m plus n. Here, instead of actual positive integers, I'm using letters that could stand for any positive integers. So anywhere in math, if you have this expression 3 to the m times 3 to the n, by this logic, you can always replace that expression by 3 to the m plus n. Conversely, if you have this expression and for whatever reasons you want to write it as this, that would be correct because this and this are exactly the same number by this logic. Now let's summarize our work, where in the next one I will in fact replace 3 by a letter A, where A could stand for any number, and that would become our exponent law. So let's work on that now. So let's summarize our discussion with an exponent law or a rule, whichever word you prefer, and a proof for it. Suppose A is a number and m and n are positive integers. Then anytime you see an expression like this, a to the m times a to the n, that is exactly equal to a to the m plus n. Don't forget, a is a number, m and n are positive integers. So this is a number and this is a number, and this is also a number. So we're really dealing with numbers. All we are saying is this kind of an expression, a to the m times a to the n, that is really exactly same as the number a to the m plus n. And the proof, we'll go over it. You'll see the logic is same as the one we used in the previous two examples. When we write a proof in math for such things, it's nice to start out with one of the expression. We don't work with both sides of the equality at the same time. Just start out with this expression, a to the m times a to the n equals. We realize we are multiplying numbers. We also realize a to the m by definition is really a shorthand notation for a long expression, and that's this expression. Since I don't know what m is, I don't know how many times I need to write out the a, so I do a generic multiply a by itself a couple of times, put a multiplication sign, put dot, and I should put another multiplication sign a, and that's m times and a to the n, unwrap it. By definition, that's really a multiplied by itself, n times. Notice the dot notation. Here I notice all I'm doing is I'm multiplying a by itself a bunch of times. So that is a times dot times a, and I have to write here how many times is that. And here's the m and here's the n. So that is m plus n copies of a multiplied by themselves. Now once again, using the definition, this long expression can be written in a shorthand way. and that abbreviation is simply a to the m plus n. So now we're done with the proof. A to the m plus n is here. So remember that a to the m times a to the n is a to the m plus n. Sometimes we say when we multiply two exponent numbers with the same base, those two exponents are getting added like this. So remember this law, practice the proof, and remember also the initial warm-up examples that are a little bit easier to follow. So remember all of this. Thank you.